Welcome to our webinar, what every plastics processor needs to know about dry ice blasting, the claims, evidence, and the science behind the process. My name is Steve Wilson, Director of Dry Ice Cleaning Applications and ESG. I'll be your host today and the speaker for the webinar. I want to thank each and every one of you for joining. I want to make note, draw to your attention, there is a Q&A tab on your screen and maybe in a drop down where you can enter any question that you may have about the process or this webinar. You may do that starting now all the way up until the end. And at the end of the webinar, we will take time to address as much of those questions as we can. This webinar is also being recorded for your future reference. If you're having trouble going to sleep at night, this might be good to pull out and help you get to sleep. But if you want to use this and reference it in the future, you may. If you want a copy of the slide deck, just email me. My email is on the last slide, and we'll shoot that over to you. We've got a lot to unwrap today, and I won't settle down on too many of these slides. We'll be going at a pretty good clip, which is why we're recording it. There are topics that could be unwrapped even further throughout this presentation. If you want to do that individually, give me a ring and we can take a deeper dive on any one of these particular aspects. But I just want to expose you to a lot of different things about dry ice blasting in the plastics industry so you can see the library of things that's available to you. So saddle up your horses. We've got a trail to blaze here this afternoon. That's some concepts we're going to explore together. I do want to give one slide to cold jet for those who may not be totally aware of what cold jet does. I want to make sure we're all on the same page what dry ice is and where it comes from. We'll unwrap the science behind how the cleaning process works. I want you to understand the fundamentals so that you know what you need to have in place in order to blast. And once you do, how do you fine-tune that blasting process for various applications you may come across in your facility? We'll explore the various claims that you hear about dry ice all the time, and we'll unwrap the science behind those. And we'll take a look at the applications that people are doing in plastics and even share some case studies of those that have had great success with it. Today, we're able to monitor not only the machine and how the status of the machine is doing, its health, but also the plastics cleaning process itself can be monitored. And we're going to take time for questions and answers at the end. Cold Jet has been in business for a little over 35 years now. It is a company that is privately held. It is a family-owned company located on the east side of Cincinnati in Loveland, Ohio, a very vertically integrated company with in-house machining. We do all types of fabrication here in our 100,000 square foot facility. And we've got multiple facilities in Europe that do the exact same thing. Cold Jet managers two different types of solutions and or machines here, high to low volume pelletizers and a full line of blasters, which can be manual or they can be fully integrated and automated. This is all we do at Cold Jet. It's not part of our business. We live and die on the CO2 molecule and making use of that. We have no other distractions but dry ice. We've got over 40 engineers in our engineering department. It's all in-house. They have over 370 global patents, which is all designed in-house, and we spend a lot of money every year, 7.2% of the budget, to keep you on the cutting edge of dry ice production and dry ice blasting. 24 hours a day, every day of the year, in more than 85 countries, and 14 brick and mortar locations, sales, service, and production facilities in 10 different countries around the world. You can contact us for customer service. We have over 50 direct sales team out in the world. We also do work with a dealer distributor network, which does a great job together with our direct sales team, servicing over 19,000 installed systems around the world. We'll come to you for an on-site evaluation, see if you're ready to do some blasting, what it is you want to accomplish, and even set you up with the performance evaluation program where you can bring a machine in-house and do some further testing. We're there to guide you from the beginning to the end. Cold Jet Connect today is a platform that allows you to monitor both the machine and the cleaning process. And let's not forget Dazzle. All 14 of our sales and service locations have a design and sample lab for customer trials where we engineer and optimize a solution for your application. I like doing things live. We can come to you and perform some testing. Many times people come here and perform testing, or if they can't come here, We will receive parts from you, and we will do a Microsoft Teams meeting or a Google Meet, and you can watch as we do some blasting live, and we're just prepared to be dazzled as you see the magic of dry ice in the plastic applications. Dry ice 101, what you need to know about dry ice blasting. Basically, dry ice is just a solid or frozen phase of CO2. It's dry because it doesn't go through a liquid state as if you were evaporating. It sublimates. So when you talk about dry ice phasing from a liquid to a gas, use the term sublimation, not evaporation. It is basically found naturally in our environment. It's what plants use for photosynthesis. We exhale about 2 pounds of it every day. The CO2 that's used to make dry ice is from numerous industrial processes, petrochemical facilities, distilleries, fertilizer plants, ammonia plants. They all give off CO2, and a gas company will locate right next to there, and they'll claim that CO2 rather than letting it go to the atmosphere. You've all heard of carbon capture and sequester. This is carbon capture and utilization. The gas company will capture that byproduct, becomes the feedstock for dry ice before it enters the atmosphere. They will purify it, so when you're out on the floor blasting, it doesn't smell like Jack Daniels or some other process. It'll go through a liquefaction stage where they pressurize it, and then you can transport that liquid anywhere to a facility that has a pelletizer. That would be a remote gas company that's going to make dry ice and sell it to many plastics processors. They make about 25,000 tons of this every day, and most of the dry ice it's made is not used for blasting. It's used in food processing or transport cooling. The manufacture of dry ice, or the production of dry ice, is a closed loop system. As we talked about, that liquid can be transported, as it's shown in this image here on the left. The truck comes and fills the tank. On this blue line, that liquid is fed, liquid CO2 is fed into a cold jet pelletizer right here. At ambient pressure, that liquid flashes into snow. About half of it goes to snow, and about half of it goes back to gas. That's where this green line comes in. This is where the closed loop comes in. Kind of resembles in-house when we mold a part and it's scrap. If we're allowed, some medical parts you may not, but if we're allowed to reclaim that, we'll put that plastic in the granulator and put it right back in the machine. We do the exact same thing with the exhaust gas. That green hose brings the exhaust right back in, repellets it, liquefies it, brings it right back into the press. So it's a closed loop system. There is a die inside that pelletizer, which the manufacturer of dry ice will select which size pellet or nugget do I want to make. 3 millimeter is the size. It's often referred to as rice dry ice. The other larger sizes are used usually for food processing, transport, cooling, some other type of use for dry ice. But it looks a lot like strand die extrusion. If you've been around pelletizers in the plastics world, it looks a lot like strand die extrusion. This is a video of what it looks like when it's in production. Dry ice is like strand die extrusion, other than the fact it's not continuous. It is a batch. The liquid goes in, flashes to snow, the cylinder pushes it through that selected die, and then out come the strands. You're looking at 3 millimeter pellets being made. You'll also observe the CO2 on impact where it's hitting the tote is sublimating. Note the gas is going down. We'll address that later when we get into what you need to blast in your facility. But CO2 is a heavy gas. It's going to go out and migrate out open doors and open windows. Just something you can observe there. But that flashes into snow because of the Joule-Thomson effect, and we press that through a die. That picture on the right side of the screen is what cold jet manufactures in addition to blasters. That's one of our pelletizers. The common forms of dry ice you're going to see are blocks. You'll see slices, you'll see nuggets, and you'll see pellets. Blocks go into machines that can shave them. Slices are used a lot of transport cooling. They're used on the carts of airlines. Nuggets are, like I said, used for transport cooling a lot. Pellets are used for blasting. There are blasters that can adapt to any one of those forms of dry ice. However, the 6x6x10 blocks and the 3 millimeter pellets are the most popular. The blocks go into machines that have shavers in them. You can put the blocks, you can put the slices, even pellets in there. And a pusher plate is going to push those pellets up against a set of blades. It's going to shave the dry ice, and you get 0.3 microparticles. You're always going to have a very small particle of dry ice. There are also pellets, 3 millimeter, which is a very common form of pellets and blasters in the marketplace today. You can feed the 3mm pellets, blast with the 3mm pellets, or you can fragment or cut it down to those small, like shade particles. The 3mm machines do not have a pusher plate. They rely on gravity to feed the pellets. Dry ice, being hygroscopic, wants to pick up moisture, can resist flow. So we have a patented SureFlow system on our machines. It's insulated, isolated, vibrated, thumped, and kicker pins. You're almost fluidizing that dry ice so that you keep it moving so that you get a consistent flow of dry ice out of the nozzle and it doesn't sputter on you. There's a lot of engineering keeping dry ice flowing. And all dry ice, just so you know, if you're in the medical business, it's all FDA 21, CFR 110, by the Compressed Gas Association standards. And many governmental agencies approve it. It's the same CO2 that's used in carbonation, food processing to control fermentations, etc. But how does the process work? Understanding the fundamentals, what do you need if you're going to implement this? And how do I fine tune it? Because I have a lot of things to do inside the shop. We're offering you more than just a machine. We're offering you a solution because you're going to see a lot of different things people are doing with this. And why is it a solution in plastics? These are the things we hear at trade shows, when I go to conferences, when people come here. These are the goals we hear. I want faster cleaning cycles. We want improved cleaning quality. I want reduced labor costs. I need an environmentally friendly, sustainable way to clean. I need multifunctionality for cleaning a bunch of different types of molds, some online, some offline. And I need to monitor the process. I'm into digitalization at my plant. Look out for those things as we go through this presentation. If we find a match, I'll highlight it in green. Let me give you some rules of thumb for dry ice blasting you can put in the back of your head and things to don't forget about dry ice blasting. When it comes to contaminants on substrates, if it's on it, it will generally get it off. If it's in it, if that contaminant is in it, it generally will not. Bluing metal, for example, because you overheated the bowl, that's not coming off. Surface rust, you got a water line leak, you got some rust on your moving platen, stationary platen, it'll take surface rust off. It will not remove the pitting because that requires profiling. You cannot get white metal with dry ice, which is good because that allows us to clean molds. Dry ice blasting is line of sight cleaning. For example, it won't clean the water channels of your mold. There are beside the press solutions for that. There are ultrasonic tanks for that. We are line of sight cleaning. We're cleaning the parting line of the mold, cavities and vents. Areas behind slides and cores and pins and bushings are going to get dirty. Eventually, you're going to have to pull the mold, take it apart, and clean it on the bench using dry ice. When uncertain about a given substrate, its texture, its surface finish, its hardness, start with lower pressures, start with smaller particles, and then work your way up. Change your design and experiment one parameter at a time, usually increasing blast pressure because we'll find out that is squared. When the contaminant is harder than the substrate, that's challenging for this process. You get dried hard glue on leather, for example. The pressures you need to get the glue off is often leaving a signature on a softer substrate. Common contaminant removal rate is about 4 square feet a minute. So if you're trying to quote a job and say how long is it going to take, you can generally get about 4 square feet a minute, but that's very dependent on the contaminant and the substrate. If you have the opportunity to clean something hot, do it. The greater the delta T between the contaminant and the substrate, the faster and easier it will clean. And lastly, more pressure means faster cleaning. It also means more noise. So you find that perfect balance that keeps production happy with speed, keeps our safety departments happy with noise. When I describe the science on how the dry ice blasting process works, I use an acronym. I use ICE. Stands for impact, cold, and expansion, which is simply my way of taking things that I read in the library from these sources, which really define kinetic energy effect, the thermal effect, and the gas expansion effect. This is the industry standards. Everybody agrees this is how the process works. The impact is kinetic energies, and dry ice particles are soft. They have little hardness or mass. As a matter of fact, dry ice has no Rockwell hardness number because it's frangible. If you go to get a Rockwell hardness on it, it's just going to sublimate on you. So we measure the hardness of dry ice on a Mohs scale of this naturally known materials to man. Dry ice is about a 1.5 to a 2. Your fingernail is about a 2.5. You may be bead blasting with plastic abrasives, walnut shells, corn shells, even aluminum oxide in a blast cabinet in the back of your shop. Those things are much harder than dry ice. Because they are soft, we got to get them traveling at supersonic speeds. upwards of 1,000 feet per second to get that momentary impact, that impulse impact, the kinetic energy effect. We can calculate the kinetic energy that's going into the blasting process. Kinetic energy is simply 1/2 mass times velocity squared. You, the operator, have 100% control of kinetic energy, and you fine-tune that process for various substrates by adapting the particle size, and you adjust the blast pressure on the machine. So you control 60 to 70% of that cleaning effect on an ambient substrate is through this particular property, kinetic energy effect. A couple other things that impact the amount of kinetic energy is maintaining a 90-degree angle. Being perpendicular to the substrate will give you the most kinetic energy. Your angle of impingement, your standoff distance can also impact. The further away you get, the less aggressive you will be, and how fast you move that nozzle. Your traverse rate will also can affect your impact and can impact the amount of heat transfer you also have. Controlling kinetic energy, being able to adapt to a variety of things inside a plastics plant is important, which is why we make machines that have programmable recipes. You can save various recipes. You can put a password on them, protect them, and you can lock out screens. Why? Because not all things are created equal in a molding shop. Some of our molds are H13, Peak 20 aluminum. They might be a Class A1 optical or a piano black automotive part. They might be a D1, 2, or 3 automotive instrument panel. It might be textured. They may have delicate features like a radiator on a fracking truck. We can clean that without damaging. That's how delicate you can be. Or some complex geometries on a mold. Is my mold a 101? I'm expecting to last 1,000,000 cycles. Is it a 105? Just a prototype tool. I just need the ability to adapt and to adjust. We have systems on the PCS Ultra where you do that. You have the ability to choose between 28 particle sizes, between 3 millimeter all the way down to 0.3. So you can control the amount of kinetic energy that goes into the process. On the screen, you see they've selected 2.5 millimeter, where they're blasting at. They're 2 pounds a minute. They're blasting at 75 PSI. That's a pretty common blasting parameter for somebody who's probably going to like clean a screw or something more aggressive. Just remember, this is what you're trying to control, is the kinetic energy, 1/2 mass velocity squared. And it does now bring what molders want, multi-functionality for cleaning different types of molds. Why do I want 3 millimeter pellet over the smaller ones? This is some benefits of particle size. 3 millimeter pellets are very good on thick and tough contaminants. You get a good flux density, but it's really good for cleaning things like ambient temperatures. You get more aggressive cleaning. Because it's 3 millimeter, you're going to feed about 1.5 pounds to 3 pounds of dry ice, and you need 50 to 150 CFM at 80 PSI. Microparticles, you can see, have a greater flux density. You're going to get more surface strikes, more impacts per unit of time, per unit area, and it's really good for thin, hard, brittle contaminants like cleaning the mold. They're quieter because it only takes 50 CFM or less. Some nozzles only require 12 CFM, typically it's 25 to 30, and it takes about 1/3 of the amount of ice. 1.5 pounds is the maximum instead of the minimum. If you were to look at 3 millimeter pellets versus the microparticles and particle size, we blasted on modeling clay, and you can see the impacts that they made on modeling clay, and then we poured a reverse polyurethane casting. And you can see on the right-hand side, 3 millimeter, but as you move towards 0.3, as you move up that scale, you see the flux density increases. You're getting more particle strikes per that square inch than you are with 3 millimeters. So when you need to get into tight, small geometry, small places, you're better off going down to the smaller particles. On the other hand, when you need more kinetic energy, you notice you get more kinetic energy as you go up. When you go to clean a screw, you're going to use the 3 millimeter side or something in between there. So there's advantages inside of a molding shop. There's times you want to go 0.3, 3.0, or somewhere in between, and then save that recipe. If you don't have a new machine that can cut at 28 sizes, you've got a couple of choices. First choice is trade the thing in, trade up and get yourself a new machine. The second choice would be use a nozzle that fragments. You can take a 3 millimeter pellet machine and you can use a nozzle that has pins in it or screens in it, and you can knock that particle size down to 0.6. So you are having somewhat control over the kinetic energy, even though you don't have a machine that can cut. If you've got a shaving machine, you're shaving blocks, whatever, you can actually take that from 0.3 down to 0.1. I would encourage you, don't try and print your nozzles, but if you've got a machine, they look like, oh, well, that's just a straw, I can do this. I would encourage you, don't do that. There is double convergence and divergence, there's axisymmetric flow, there's MERN technology in there. You've got to make sure you have uniform distribution of particles. They're all going the same velocity across that nozzle, delivering the appropriate pellet, and not even damaging the particles going through the nozzle. We have that in spades here at Cold Jet, so just buy your nozzles from us and don't try and print them, which gives you multi-functionality for different types of molds. This is Chris Schaefer. If you're in the middle of the United States, Chris is your guy. He is blasting as gentle about as you can get with dry ice blasting. That's the 0.1 particles, and he's taking letters off of a business card without damaging the card. So I can clean some very gentle, delicate molds. On the other hand, there are times I want to clean a screw. I need to be more aggressive, but not abrasive. For example, this is an asphalt truck, and we're going to just take 3mm pellets. We're going to put 3mm pellets in. We're just going to leave them at 3mm pellets, and you're going to get a much more aggressive, yet not abrasive clean and move very quickly. You'll note the dry ice is sublimated. It's going to a gas. It looks like the asphalt's disappearing. It is going to the ground. The contaminant does not disappear. But you can see you can be aggressive when you need to. You got the impact, we move to the cold, so the path to cleaning with dry ice is cold. That's the whole idea of it. It's what separates us from other blasting methodologies. It's minus 109 degrees. That delta T between the dry ice and the contaminant causes the contaminant to brittle. It shrinks, loses its bond strength with the substrate. Studies, once again from James Snide's library reading materials, show at 500 degrees C, which is not likely to happen in the molding world, but thermal properties contribute up to 50% when the mold is hot. Anecdotally, you're going to say, man, I've cleaned things hot. They seem to clean better and they seem to clean faster. This is why. The thermal effect is contributing more on hot substrates. So that rule of thumb, if you get a chance to clean it hot, do it. Operators really can't change the temperature of dry ice. It is what it is, but you can control the amount of thermal transfer by how fast you traverse, your dwell time, and the feed rate, how many pounds per minute you feed into the process. If you've ever received an email from me, it'll say on there, we make cleaning cool. Dry ice really makes cleaning cool. It's a fun job to do, and it is in the summertime a nice cool breeze. The last thing that makes this process work is the expansion. It's a unique characteristics of dry ice over other media. On impact, dry ice phases back to a gas. It sublimates. Volumetrically, it grows about 800 times in size. Multiple explosions occur on the surface during that sublimation. You're lifting off or blasting the contaminant from the inside out. You really don't have control over that unless you want to change atmospheric pressures. You want to go up and blast on the space station or something. It's going to be about 800 times in size. This is what it looks like. The contaminant is in red. It's being micro cracked with the impact. It's being shrunk. That bond's being broken with the cold. It's being blown away when it sublimates with the expansion. That's the dry ice cleaning process illustrated on a red contaminant hitting the substrate, shrinking and blowing it up. What do you need if you're going to operate one of these things? Well, the first thing you need to do is get a blaster. The picture on the right is a guy heading out to the shop. He's probably come out of the tool room. He's got a machine that shaves blocks, so he's going to be blasting 0.3 particles. If he wants to get more aggressive, more kinetic energy, he's got one option: turn the pressures up because the mass is going to be consistent, 0.3. He's got his little cooler down here. He's got his dry ice. Looks like he's got some tools in his box. He's probably got some lube. He might pull some PM on the mold after he gets done cleaning it. He's ready to go. Compressed air source, you need to understand the air requirements in your shop. Each one of these nozzles in here requires a different CFM at 80 PSI. 3mm platforms want 50 to 165 CFM at 80 PSI, and they want a 1-inch air line. Almost every nozzle in here is that way, except for these maybe 8 to 10 across the front row. The Microparticles 0.3 systems only require 12 to 50 CFM at 80 PSI, and they can hook up with a 1/2-inch air line. I've seen them hooked up with even smaller. I've got to run into 1/4 inch. Just know that if you go less than a 1/2 inch, if you ever come up short, sometime that's your stall point. You're feeding a fire hose with a garden hose. You just need to get a bigger air connection, get up to a 1/2 inch. These systems use your air supply. There's no pump in there, so you set your machine at 80 PSI, you pull the trigger, it drops to 50. You don't have enough air to run it. You need to pick a nozzle that has a lower CFM rating. It's like horsepower and torque in a car. So don't expect a pump. There's no pump in the machine to build it up. Most of us are familiar with ISO 8573-1, just typical plant air, refrigerated class 3 air is great. In my demo area, we use class 2 desiccant because from time to time I got to clean semiconductors, things that are really sensitive. And there is a filter on the machine. The CFM ratings are at 80 PSI. If you go lower, it's less CFM. You go higher, it's more CFM. You need to pick a local gas supplier of your choice. He'll ship you 550 pounds of dry ice in a tote, looks like that. Lindy Air Gas, those companies listed there are where you're going to get it from. If you're welding in your company now, you probably already have a dry ice supplier and didn't even know it. That box is about the size of a Gaylord. It's going to last 7 to 10 days, and that dry ice will sublimate up to 4% per day. You get to where you're going, you need to plug it in, 110 volt connecting electrics, 230 in Europe, single phase. Although we do have a machine that's all pneumatic, but not overly used in plastics. And PPE, safety glasses, glove, and foam earplugs. Noise is a function of blasting pressure, your pellet size, your nozzle selection, what's your substrate look like. If it's got orifice, it's going to whistle. How big is your room? Are you inside or you outside? There's always a trade-off between how fast I clean it at higher pressures and slower cleaning at lower pressures. Do you need to blast at 100 PSI? That's up to you. Just know, most of us know OSHA will allow us to be exposed to 8 hours of 85. So it's less than 90. Rule of thumb, safety glasses on people within 10 feet of where you're blasting, earplugs within 30 feet if you're at 80 PSI. It doesn't have to be loud. We blast it on the trade show at the floor. This young lady in the picture is the president, CEO, owner of a plastics molding operation here in Ohio, and she's had a blast with cold jets. She's cleaning a 9-cavity O-ring mold on a show floor. She is cleaning with microparticles about 30 PSI. And it's very quiet. It doesn't have to be loud. Typical plant ventilation is typically perfect in your shop now. You're already doing quite well because we're processing plastics. But if you get into a confined space, just make sure you're turning the air about 4 times per hour. You're going to put off about 8 cubic feet of gas for every pound that you blast. And there's a whole presentation on that. There is a OSHA requirement to be exposed to no more than 5,000 parts. Right here, the 0.5. The higher the concentration, the shorter the duration you're allowed to be exposed to it. You're probably sitting in a room now, it's probably 600, 800 parts, and when you blast, usually if you put a monitor on the wall, you're going to get an alarm at 5,000 parts per million. You're ready to go. So get your blaster, run out to the shop, and start cleaning molds. You are all set. That's what you need to make sure you have in place before you blast. Let's look at the various claims about dry ice blasting, what's going on in plastic, what supports those claims that we all talk about. It's good for the E, it's good for the environment, it's good for our OEEs. You're going to note, observe, I'm talking a lot about injection molding applications just because it's a discontinuous process. It's easy to interrupt, but all types of processors, extrusion, blow molding, thermoforming are using this in the plastics industry. The first claim is it's sustainable, and that's for some an elephant in the room because it's a society. I thought we were supposed to be getting rid of CO2, right? We're supposed to eliminate that. And you're telling me that dry ice blasting is good for the environment. The dry ice blasting is a sustainable process because it's carbon capture and utilization. We unwrap that, but I just want to remind you that factories give off CO2. That circle here is there's a lot going on in there for the gas companies, but they liquefy it and they turn it into dry ice. It's a byproduct that processes it. That CO2 would have been discarded. Now it's given a second life. It's a closed loop. It doesn't produce more CO2, and it generally replaces cleaning methods that have man-made fluorinated gases in them. We're just using nature to clean. When you blast with dry ice, that is open loop. But regulatory agencies have spoken about blasting with dry ice. If you're in California, due to the fact that dry ice is recycled, it will not contribute to your greenhouse gas score. It's already been accounted for at the producer level. Don't count it a second time. The EPA has a mandatory fact sheet. It's 40 CFR Part 98. Dry ice blasting is not part of that. Why not? Because you're not going to get to the threshold that they're monitoring people at 25,000 metric tons. That's an extremely large amount. So we have a communication from the EPA that users don't have to report it because you're not going to hit that threshold of 25 million metric tons. So they're telling customers under the current program, blasting doesn't have to report. And these are the agencies that keep us safe and that have things to say about dry ice. If you want to see what that report looks like, this is the metric 25,000. I highlighted a couple areas. A guy who cleans for a living may go through about 1,000 pounds a day, may go through 2 of these totes. If you're going to hit that 25,000 metric tons a year, you're going to have to go through 274 totes per day, every day of the year. That's very unlikely. And customers tell us that it supports their environmental program. This is a guy from Gobbert, environmentally friendly, sustainable cleaning. Also, Electrolux supports their environmental initiatives. They're using it to remove foam that extrudes out of orifices when they insulate refrigerators. Sometimes it's not the efficiency of the cleaning process, but it's a safety and environmental compliance issue that's driving the solution. And for Electrolux, it was part of their overall initiative to become environmentally free. And that's one of the things we do. A. Raymond says the same thing. It's environmentally friendly because it's helping reduce solvents for them. And the same thing at Miniature Precision Components, increase employee safety. Dry ice is non-abrasive. I'm going to fly through this, but I'll give it to you if you want in more detail. I'm talking about extending the asset life of the mold. Poorly maintained molds just simply wear out faster as they get dirty. But you'll hear people in the dry ice industry, the blasting side, saying, well, we're nowhere mechanically, we're no stress thermally, and we don't wear things out chemically. Prove it is the point of this. One of the things to take a look at is for compressive components. I borrowed this from the Tooling Docs guys up there, and it talks about getting the wear out of mold cleaning. These are charting mold wear. You see the 4 things in red that contribute to mold wear. Most of these are dealt with when you design a mold. You pick the metallurgy, you pick the coatings, you pick the process. But when your maintenance practice come into play, your cleaning technique can contribute to mold wear. So let's get the wear out of mold cleaning with these old traditional breed. The more this guy in this picture on the bottom right, the more he wipes that mold, the more contaminants he picks up, the more abrasive he becomes. So what's your mold worth? How long do you want it to last? It's extremely difficult. Once you wear that mold out, you're starting to get a little bit of flash. It's very difficult to process around that. You're just going to mold the most consistent scrap you've ever seen. So extending the life of the tool can be a real time saver and a cost saver in the long run. How do we have proof? We gave a machine to Kedem University. Chuck White is the metallurgist. He gave this to a class of failure analysis grads. I love that class where we try and destroy things. They grabbed a variety of materials from very soft, commercially pure aluminum to some pretty decent 4130 at 79 Rockwell. They fixtured a wand at 1 inch, 25 millimeters away, stuck one here at 45 degrees. They stuck one at 90 degrees as well. Then they did some testing and they came back after blasting 60 seconds in the same place, which is not how you clean something. It's not working if you did that. But they stayed at 90 degrees for 60 seconds at 1 inch away, and they said the sample had no damage, and they tested in microinches with a profilometer. So it's gentle. That's some of the science where we say it's not damaging. There's that. And also from books in the library, cleaning with dry ice does not damage most industrial structures because its particles are relatively soft. So there are some science out there. No stress thermally. So bring the degrees of your mold. This comes from James Snyder, an independent researcher. Once again, library material. You can jump right to the conclusions when he tried to measure thermal stress in dry ice cleaning. The temperature decrease across the surface only is one of the big reasons there's no chance of thermal stress occurring to the substrate. He blasted across this surface right here after putting thermocouples flush and at different depths all the way down to 2 millimeters. He swept across for 30 seconds, which for a piece that size is a pretty long time. The 2 millimeter depth thermocouple dropped 10 degrees after 30 seconds, illustrating the thermal effect only occurs at the surface of the mold, no detrimental effect on the mold. He did one when the mold was hot because they had some people in the rubber industry, so it was 300 degrees hot. The temperature differences between hot mold and cold dry ice will not cause cracking. For the reasons he talked about, it's at the surface, and he went ahead and he calculated the thermal stress by capturing the temperature, Young's modulus, coefficient of expansion, Poisson's ratio, and found, man, that the amount of stress we're generating is less than when we heat treated it. So he said, go ahead. You can use this process on a wide variety of things without damage, from brass, beryllium, aluminum. Go ahead. You're not going to damage it. That's where it comes from mechanical and thermal standpoint. It comes from independent studies that have been done. A customer did their own on thermal shock. They did their own studies on stainless steel 440C. After blasting on them, they found unaltered carbon particles, both at the core and the surface. After they did those tests, this customer put dry ice blasting to clean injection molds in 17 facilities around the world. There's nowhere chemically, dry ice is what CO2 molecule. It's a linear molecule. It's non-polar. It's not bent like a water molecule that will react with the mold. You get water in your mold, it's going to react. It's going to cause it to rust. There's no charge to this molecule. It's linear. It's inert. It's non-toxic. It just doesn't react to anything. So impact-wise, thermal-wise, chemistry-wise, it's very good for cleaning tools and not causing any damage. That's the science behind it. Sometimes we have plastics that are abrasive or corrosive. You might have a coating on your mold. There are so many different types of coatings. But Sulzer Metco has a presentation. These are slides. That's the opening title slide from now Orkalon Balzers. This is their reasons why they put coatings on, slide number 2. By the time you get to slide number 60, they've realized that, hey, you're running this mold, it's getting dirty. How are we going to clean it? Slide 61. Hey, have you considered dry ice blasting from this company called Clogged? They actually want you to clean molds this way. We have molders out there cleaning Class A surfaces, highly polished reflective surfaces. He's fragmenting dry ice down to 0.6. We talked about in the Kettering study and James Nye study, go ahead and blast on aluminum. That's a blow mold with its aluminum and it's got a beryllium insert. No damage being done. We have customer testimonies like Tom Mendel at Performance Plastics, who has since retired. If you want to reach out to them, it's now Chris Lawson. Cleaning will not destroy parting lines, change or destroy the metal. Just as an FYI, this company runs a lot of engineering grade resins. They run peak fluoropolymers. Their molds are 500 degrees hot. They have oil temperature control units sitting on the non-operator side of the machine. If you worry about cleaning things hot, these guys do it every shift, every day. The process is quick and dull, doesn't dull tools. That comes from miniature precision component. It improves quality, your OEE scores. It's good for the ease. This is unpredictable mold cleaning maintenance. Have you ever tried to clean a mold like this? 128 cavities, face the difficulties, remaining focused and consistent. Might be pretty good on probably the first half of the cavity, but the back half, I'm just trying to get done. It's just not accurate and it's not consistent. You're going to make better parts. One, because the dry ice is all food grade. It's not going to cross-contaminate medical parts, which mostly comes into play if you're deburring or deflashing a part, or if you're molding a medical part and you're cleaning with something that has a solvent in it, and you have to do a secondary clean with alcohol. And if you don't, you're just going to go ahead and throw away the next few shots to get rid of that residue. You don't have to worry about that with dry ice. They're going to get a better clean because dry ice is that small microparticles gets into complex geometry. Dry ice also has a lower surface tension than water, so it's able to get into places very easily, and it can do its work and clean. And we want to keep mold cavities and vents clean because not all polymers, if I make scrap, not all of them are easy to recycle. Your thermosets, they cross-link, you're done. Your LSR is the same thing. Higher quality parts means an improved OEE score. It's just one of the reasons you make better parts is when you get this system and these types of systems in play, it's just more conductive to proactive cleaning versus firefighting. It just causes unexpected production delays, time, money, just keeping vents and cavities clean. A lot of problems happen, and we all know the cost of this. When you get parts turned back, they'll send the whole batch back. Remember this first one, short shots and clogged vents. These are things you can prevent according to Sun Microsystems and Structural Defects Manual and FemTech. You get a clogged vent, you can get a short shot. You get flash because of a clogged vent. You get a clogged vent, you get burns. You get a clogged vent, you get mold damage. I mean, that air has been trapped in the mold, it's jetted or dieseled, it's actually turned it blue. That's one of the rules of thumb for dry ice. Dry ice is not going to get that bluing out of there. Dirty mold cavities because of played out. Dirty mold cavities cause contaminations. Dirty mold cavities cause splay. Clogged vents cause weld lines. Multiple problems, one simple solution, clean the cavities in the vents. And we've got a lot of process-driven things in molding. Let's make cleaning the same way. This is a slide I stole from Dave Hoffman at the American Injection Molding Institute, which was one of their partners. But it's a troubleshooting guide that's very common in the plastics industry. So keep your mind on short shot. You get a short shot, there's 12 things the guide tells you to do. State-of-the-art troubleshooting guide, 12 corrective actions. 8 of them say change the machine variables. 3 of them say change the size of your gate, your sprue runner, your vent. That's not easy to do in production. The first 11 steps are not corrective actions or root cause analysis. The last suggestion, number 12, says clean the vents. That is the first thing that we should do because it's the easiest thing to do. And it prevents those molding problems we just went through. So don't postpone cleaning cavities and vents. Don't wait until somebody walks up with a part and says, is it okay to ship this part? And you know it's not, just because somebody postponed it. I like to say, kill the spider, just don't knock down the spider web. These are some actual data. I know a lot of the guys in the room are really good for data. This is a custom molder sending us their KPIs. This is defect quantity before and after they started cleaning with dry ice, total weekly production before and cleaning with dry ice. Look at those screens, look at those bars. Note the process control improved across the board. The upper and lower control limits shifted on every one of the matrix, and the overall consistency got better. The scrap rate went from 1,866 to 803. That's a 57% reduction in scrap. The weekly production went from 174,000 to 216,000, a 24% increase. The scrap rate went down. They got more good parts, all because they started cleaning the mold consistently with dry ice. That's improved quality cleaning. This is the same guy who's tracking scrap rates. Scrap rate went from 1.8 to 1.3, just because they started cleaning the mold. And customers tell us that. People are like, deal, decisive influence on the quality of our products. This is a guy who had all kinds of problems with parts. They couldn't figure it out. It says the plastic machine manufacturer couldn't figure it out. It was their resin supplier says, if you try dry ice clean, these guys are molding some very small parts, and they went from cleaning at 16 hours to 1 hour. That's 400 more hours a year they got back, a 10% improvement on their OEE availability score, 500,000 more parts per year, just because they switched over to dry ice. That's improved cleaning quality. It definitely affects the results in superior clean. That's what Husky tells us. That's a preform mold, some very complex geometries to clean. Once again, this is Sylvan PET molds, complex geometries. They went from 2 to 4 hours in cleaning time down to 30 minutes, and it gives them the ability to meet the high cleaning standards their customers demand in a preform. That's improved cleaning quality. It increases productivity. Notice 60 to 70% of all mold maintenance is cleaning, according to Steve Johnson at Moldtrex. Why not do it faster? We just showed you how to improve quality. And usually when you go faster, you sacrifice quality. It's not true with dry ice. You're going to go out to the machine, open the gate, clean the cavities and vents, and I get you down to an area, a very small micro molding, give me about 1.5 inches, 2 inches, I can get you clean. This is the guy that went from 45 minutes to 3 to 4 hours down to 45 minutes. Every time he had a shutdown before, they were losing 375,400 preforms. Much faster. Downtime was measured in hours, now minutes. This is what it kind of looks like in the plastics. When you're cleaning cavities, you're cleaning the A half and the B half. That's a class A surface. You see the contaminants being removed. That's a microparticle 0.3. That's about a 30 CFM nozzle. He's probably about 50, 60 PSI. And he's cleaning off gases off of a mold. This is the other half, the B half of the tool. You can see the contaminants look like they're disappearing. They're dropping to the floor. Sometimes if you're running a white part or a clear part, or you're running a metal injection molded part, you might have a binder that's causing a waxy substance on the mold. You might have to automate the cleaning cycle more frequently than you would cleaning thermoplastics. You can automate this if you have to. Marcotte went from 4 hours down to 5 to 10 minutes, reduced their cleaning time 95%. That's an improved availability OEE score, maximize their assets. So time is money. All right, this is Marcotte. It went faster. This is Tyco Electronics, went from 6 to 12 hours down to 1 hour. Very complex geometry molds with connectors, not easy to clean. But when you go from 12 hours to 1 hour, that's a tremendous availability score OE improvement, faster cleaning cycles. This is a good thing if you optimize your cycle. How about optimizing your cleaning cycles? You're doing great out on the track, you're doing great on the production floor, but how are your downtimes? How are your pit stops? How are your availability OEE scores? If you're cleaning this way, it's like pit stops back in 1950, where they were excited to do a pit stop in 67 seconds. It's like Marcotte, they were excited to do 4 hours. Tyco was comfortable in 12 hours before. But today, things have changed in racing. A Formula One pit stop is 1.92 seconds now. It's not 67 seconds anymore. So these guys all switched over to dry ice. Marcotte went from 4 hours to 5 to 10 minutes. Tyco went from 6 to 12 hours to 1 hour. So the question to ask yourself, am I still down cleaning molds while my competitors are out running, making preforms or parts? We're not going to be able to compete using old school cleaning methods. So sometimes it's the cost of inaction that needs to be taken into consideration, as well as the ROI. If that's still you, it's time for a change. If you're in a clean room, class 100 clean rooms, we do perfectly fine. This is blasting in a class 100,000 clean room at ISO 8. You can see the 5 micron particle test. We're well below the room requirement, even well below the requirement for an ISO 7 or class 10,000 clean room. If 0.5 micron, we've still passed in an ISO 8 clean room, it would have failed in an ISO 7 clean room. And we're working on a contaminant containment nozzle for that. Sometimes people in plastics are deflashing. If you want to lower scrap rate, you want to improve worker safety, you can deflash. This is what it looks like to deflash. It can be done manually. It can be done semi-automatic or completely automatic. Flash is typically done with dry ice. Typically, they're thermoset parts, which always have flash. Occasionally, there's a thermoplastic part. The system shown on the right is a fully automated system. That's a cold jet pelletizer that has a pelletizer and a blaster combination. And it's one machine sitting between 4 injection molding machines servicing deflashing thermoset parts. This is one machine servicing a 4 cavity. This is a thermoplastic part, but it's got parting line flash. These blue nozzles are blasting the dry ice onto the parting line. The blaster's up in the upper right-hand corner, and you're removing parting line flash. It then indexes up to the gate cutter and puts the parts on the conveyor belt. But you can remove parting line flash. Sometimes the nozzle is in the hands of the robot and removing flash for a variety of reasons. We have flash, mostly thermoset parts. If you machine parts, we can take burrs off as well. They're typically high value, low volume parts, medical parts usually, PEEK and a variety of materials. This is what it looks like to remove burrs from various polymers. The burrs do remove pretty much in a flash. I'll let it go for a couple seconds. There's a couple different types of burrs on here that are being removed. The perimeter of these gears, you can see the dry ice is removing burrs without altering the machine finishes or chamfering the edges. You're simply removing the excess unwanted material and saving that part. Just for reference parts, I'll give you a go, no-go scale. You're going to deflash parts generally on the kinetic energy side of this. The thermal effect can assist, maybe even brittle sometimes to get to the TG point of the flash. Polymers about 85 Rockwell R and above do well. Those below sometimes absorb kinetic energy and they struggle. And depending on how long you stay on the part, how much thermal properties you put into the part, grab your material property guide and look up the thermal properties of the resin. Ford saved $2 million a year deflashing, switching over to dry ice, removing labor parts. Screw cleaning is very popular in the plastics industry. It can be hit or miss. Cleaning it hot, cleaning it ambient. Is the screw coated? How big is the screw? Where are the flight depths? Is the screw coated or not? You know, it's a material, crystalline amorphous, even that can come into play sometimes. That's what it would look like to clean a screw hot, although that's a blown film die, but that would show the polymer just removing very quickly off of a die. This is cleaning the screw at ambient temperatures. That is a microparticle system. They're getting away with microparticles on this one because it is a coated screw, and that's the metering section where the contaminant is pretty thin. When we got down to the transition section, it slowed down quite a bit, and we switched over to a 3 millimeter nozzle platform. Extrusion solutions, you clean dies as long as they're split, you can open them and you can get to the flow lines. Cleaning cooling rolls is very popular in the extrusion industry for sheet extrusion, whether they're just straight chrome plated or whether or not they're embossed and highly polished. Cleaning the breaker plates, very popular in the extrusion side. If you're into additive manufacturing, you're 3D printing, we do a lot of post-processing. Generally, it's powder removals or support structure removals. In this case, on an HP printed part, it's powder removal. Very gentle enough to remove the powders without damaging the printed part. So If you're doing some 3D printing, you can look at the dry ice as a way to do some post-processing. You can see these particular parts sent in by Hewlett Packard. They had sent these in. You can see some very delicate features on this particular when powder was removed without damaging some of these delicate features. This one has a lot of delicate features. The before and after for an SLS printed part for powder bed fusion, post-processing, getting rid of the powders without damaging all these integral structures. Lowering costs is like going back and referencing doing things the old way. But if you're wasting 15 minutes a day and you have 20 machines in your shop and you bill $50 an hour, you're wasting $63,000 a year. That will buy more. You'll have plenty of money left over if you buy the most expensive glass in the world. The cost of inaction, sometimes it's worth getting into dry ice blasting. So follow the money, bring some value in. Also, if you're cleaning like this guy, and you may have the EPA going, why are you using these types of aerosol cleaners? We want you to get rid of that. Well, they're cheap. Well, come to find out they may not be. This company spent $56,000 a year. Didn't realize it because these things are just expensive. Buying a skid at a time, nobody's capitalizing it. Went back and pulled a year's worth of expense cost, $56,000. They bought a dry ice blaster, amortized at $6,100. You're saving money by switching over. And people tell us that. MPC tells us it helped us improve productivity, that helped us cut costs. If you're cleaning parts before painting, you can regain your floor space. You can lower scrap. You can get rid of the drying oven. You can get rid of parts that might have not have dried and are wet. You use a combi system with a robot. You make dry ice on demand and you blast and you keep parts dry before you paint them. Get rid of aqueous cleaning methods. Last but not least, as we land this plane, I'm going to hit through just a handful of quick slides on you can now monitor the process. ColdJet Connect brings you intelligence. Data is good. Data is just an individual observation, a truth from a given point in time. That's where it starts. That information is a useful collection of data, but intelligence brings that all together and creates a narrative that lets you make a better decision and surfaces problems where people can solve them. That's what ColdJet Connect does for you. It allows you to monitor the machine. How is my machine doing? How is the process doing? How long is it taking? How much ice are we using? What's the setups? You can observe all that remotely from your desk, not without software. You just visit the cloud. From your desk, you're monitoring the machine and the process. So from your desk, you can sit through, see how the machine is doing. He's looking at runtime, feed rates. He's looking at how much ice they've used for the month. You can just look at the machine and just make sure that it is doing what it's supposed to be doing. When it needs service, I can remotely see the machine. I can help you troubleshoot it remotely. We can do chat functions, request forms, virtually guided repairs. You need to see some videos on training. You might need to go back and grab the manual, scan the QR code on the side of any one of our machines. You're going to find digital assets at your fingertips that will help you become a better dry ice blaster. You can subscribe to ColdJet Academy and get weekly updates on tips on being a better blaster. You can monitor the process and just see how you're doing after every time you blast on a weekly, monthly, quarterly, annual basis. Understand what's going on out there in the blasting floor. Make sure your schedules are optimal. Maybe you don't need to schedule 4 to 8 hours anymore. You're down to 1 or 2. Just the ability to monitor the process. For example, this guy, we need to find out why this guy cleaned a lot more in September of 21 than October of 21. You may not have known that he did that, but this gives him reports. You get some insight for that. Where do we go from here? I hope you've seen an idea that we do clean faster, improve cleaning quality, reduce some labor costs. We're clicking the boxes on things that molders want to see to make their molding facilities better. This helps with that. So we're going to take some time for some Q&A. I'm going to try and scan over to the Q&A tab and see if I can look at here. It says, how do I test one of these systems in my facility? That's a great idea. If you want to test one of these in your facility, just reach out to us at ColdJet. We will get you in contact with regional service directors. They have local assets. They will come visit you, do an on-site evaluation, and then bring equipment, do the testing for you. Is it possible to get condensation on a substrate? I blasted once and I created some condensation. I flipped the applicator over to air only and blew it off. But what happened? It is possible if you blast on a small piece, like this guy's probably blasting on a component of a tool. If you stay on it long enough and you get the temperature of that substrate below the dew point for that given day, it's possible to create condensation. Flip the applicator over just as he did. Flip the applicator over to the number 1, that's the air only setting, blow on it, and it'll quickly blow it off and you'll be good to go. Is there a possibility for generating static when you're dry ice blasting? It is possible. You are moving a dry media with dry air. Very similar when you're moving resin from a hopper through a hopper loader into a hopper, you're running a bonding or grounding cable along that. We do the same thing. When you're cleaning the mold inside a machine, the mold is mounted to a platen. The platen's mounted to a machine, and the machine is earth ground. So it's already the static's got a path to go. You'll never know you're creating it. If you're holding something that's conductive, not an insulator like a plastic part, if you're holding a metal part in your hand and you blast on it long enough, you can create static, and you'll feel it. It's like walking across carpet in the wintertime to get a static charge. Every machine has a static connecting cable to it. So if you're in that condition, you clip it on there and just give that static a path to go. What type of nozzle equipment can be used for a 3/4 inch air line? 3/4 inch air line is probably sufficient to run almost the entire breadth of nozzles that we have, particularly if you're down into the 50 CFM nozzles. If you get into the 5 series of nozzles, the high flow nozzles, you might be restricted a little bit. But for a 3/4 inch air line, you're going to be able to run quite a bit of nozzles. Is this webinar available offline to share later with coworkers? Absolutely. We are recording this webinar. And you can have that recording to show. If you want to host a Microsoft Teams meeting, I'll do this live with you and your team. If you want the slide deck and you want to present it to your team, I'll send you the slide deck and you present it to your team. So yes, I will make this available to you. This is something that's being done for educating the masses. So I want to make it available to all. Are there more questions on there? Does that pretty much get them? I think that gets them. We are 2.5 minutes ahead of schedule. So that's a good thing, I suppose. Let me go ahead and stop the recording. Oh, you got more questions before? How much time do I gain cleaning the mold hot instead of cold? It would be a guess, depending on the contaminant, but I'm gonna say it could be upwards of 50% faster. You're gonna be perfectly fine cleaning the mold on a bench. It's gonna work just fine at ambient temperature, and you're gonna get a really fast removal rate. But if you clean it online while that thing is still at operating temperature, depending on what polymer you're running, the thing's probably 140, 150, it could be 300, 500 degrees. You're just going to see that it cleans faster, probably upwards of 50% faster. So if you get a chance to clean that mold inside the press, you'll not only save that downtime, but the clean will be faster. But it works just fine on an ambient mold. Based on the studies you shared, have you seen any effects on straightness of the item being cleaned, which can cause dimensional changes, referring to thinner plates? We have not, based on studies we have. The thinnest plate that I could probably, didn't do it here, if we were doing a fracking industry presentation, I would show you cleaning radiator fins. Those are very small blades, like on your air conditioners. The fins of a radiator are small. We do not bend those. I've dealt with some very small blades and connector molds and other molds. That's where you want to use the microparticles. Can I damage that type of thing with full 3 millimeter? Yes. This is where, starting on a substrate that I'm like, hey, is this thing going to take this well? You start with small particles, you start with low pressures, and you work your way up. So thinner plates, you just got to do it with lower pressures and smaller, the microparticles. What happens if you have oil or grease on the mold surface? Does this get removed or blown around? Very good question. The viscosities of grease and oils, because they're low viscosities, when I have grease or I actually clean things that have been pickled in oil, you want to be very methodical. One, if there's that much on there, you might want to put some corrugate or plastic to catch the grease as you remove it. But you're going to want to start at the top, and you're going to want to push it from top to bottom. And when you get done doing that, it'll be white glove clean. But if you come at it at a 90-degree angle, it's just going to starburst on you, and you're going to chase that oil, you're going to chase that grease all over the place. So that's a very good question. You may want to leave the ejector pins and things like that retracted. You will remove any lubrication on those pins if you blast them. I think that's when that guy was going out in the shop. He probably had a lithium grease bucket with him. Maybe he's going to clean the ejector pins. But yes, if you're not methodical, putting the nozzle on like about a 45-degree angle and moving it methodically top to bottom, it will just get blown around. What type of PPE is required when using this equipment? You definitely want all PPE. You're going to want to wear safety glasses. You're going to want earplugs. If you're going up really high pressures, and then some of these machines will go up to 240, 300 PSI, you might want to put some earmuffs on top of your earplugs. You're going to wear gloves. Any type of thermal glove is fine if you're going to handle the ice. If you're just holding the applicator, any one of your work gloves is absolutely fine. But if you're going to handle the ice for any period of time, a thermal glove is better. It's not a trip to the hospital to touch dry ice. It's something that I don't encourage, but I mean, even as an adult, I still run my finger through a candle every once in a while, but I don't stop, and I don't squeeze dry ice. If so if in my bare hand, if I keep it moving, like running my finger through a candle, it's okay, but it's not a practice that I would encourage. If you're going to pick up dry ice, you definitely want to have a glove on, a thermal glove. What other questions might we have? Those are good questions. We're right at an hour. Oh, all right. I'm being told that is it. So I'm going to go ahead and exit our webinar. I want to thank you all again for attending. My email address is on there. If you come up with a secondary question, or if you want me to share this with you, please email me at swilson@coldjet.com. Please visit our webpage, go back and look at all the different applications. Maybe you do more out there than just plastics. The principles we went through still apply to you, but there are all types of industries and applications that are unwrapped on our webpage that'll guide you to the best machine and best solution for you. So once again, thank you for attending. I really appreciate your time and effort for taking the time out of your schedule, and thank you. Appreciate it. Thanks.